All right, this video is to help you with the calculations in this advanced study assignment. In this experiment, a student weighed out 0.207 grams on a analytical balance, used all the digits. This metal was put in a little gelatin capsule, put in a large test tube, and dissolved with 6 molar hydrochloric acid. The tube was sealed, and eventually the capsule dissolved, and the aluminum alloy zinc compound was dissolved, and hydrogen gas came off. And that hydrogen gas pushed a bunch of water into a beaker. That's called displacing. The displaced water was 225 grams of water. What is the volume in liters of the water displaced? Because that'll tell us how much hydrogen was produced in volume. Well, we know the mass of the water, 22.5 grams. That was measured on a top-loading balance because it's too heavy for an analytical balance. Looking at the last page of the lab directions, you can see at 22 degrees, that's going to help us set what the density is of water. We displaced 222.5 grams, and at 22 degrees, the density of water is 0.99773 grams per mil. We can use that density to figure out the volume of water, 223.0 milliliters. You can see the calculations. Convert that to liters, because we're going to need that in our calculation for moles of hydrogen. So that's the answer for number 1. Now you're going to get different numbers, so you don't type in my numbers. Do your own calculation. The second question is to figure out the pressure of hydrogen in the experiment. What we need first is to know that there's water pressure that's part of it. We can figure out the pressure of water, the vapor pressure of water, by looking it up on a table based on the temperature. So this is the same table that the density has. So we're going to use the other number that's in the middle of the column, 19.8, as the vapor pressure of water. We need to subtract that out. So in number 3, the total pressure inside our container has hydrogen gas and water in it, but we need to subtract out the water pressure, which we just figured out. All of this is in equilibrium with the vapor pressure, the barometric pressure, which is 745.1 for this experiment. So we're going to subtract out, by solving for P, the pressure of hydrogen, and rearrange the equation given so that we can isolate the pressure of hydrogen. So we need to take the barometric pressure minus the vapor pressure of water that we determined in the previous problem. It gives us 725.3 millimeters of mercury. However, for our calculations, we need it in the unit of atmospheres. So by dividing by 760 millimeters of mercury, which is a perfect conversion, we find it's 0.9543 atmospheres. 1 atmosphere equals 760 millimeters of mercury is perfect. We don't lose any sig digs. So our answer is 0.9543. You can see the calculations there. Question number 4 was to figure out the temperature of this experiment. Well, it's based on the 22 degrees Celsius that was measured by the thermometer. Now, convert to Kelvin is 273.15. 293.15 is what you get on your calculator, but we see this is an addition problem, so we need to look at the least accurate position. So we're going to have to round to the tenths position because of the thermometer reading is less accurate than 273.15. So the rule of addition means we got to round to the 0.1 position. So we got to round that up to 295.15 because it's a perfect 5 for dropping, and we round to the even numbers. So 295.2 Kelvin. We'll need that for our calculations in this problem right here. In order to calculate the moles, we're going to use the ideal gas law, PV equals nRT. We're going to solve for N. But we need T, temperature, P, pressure, that we've already calculated. R is given in the problem. And V, volume of the displaced water, is the volume of hydrogen. So I plug that into the ideal gas law that has been arranged to solve for moles of hydrogen. You can see I plugged in the pressure and the volume divided by R divided by temperature. Make sure you can calculate this type of number and get the number of moles. I entered it here as an E instead of writing that times 10 to the minus 3. The computer can't recognize that. It can recognize 0.008785 or the number as shown. Now, in order for this experiment to work well, we actually need to take that moles of hydrogen and find how many moles of hydrogen are produced per gram of alloy. Now, we weigh out less than a gram, So we're going to divide by the mass that we use. This is found in problem, the first question. So I take the moles of hydrogen that was just calculated and divided by the mass of the sample. And you can see that I get 0.04224 moles per gram of sample. So that's my answer for number 6. Now, because of that, I can use that number to calculate the percent aluminum in the sample using the calculation based on equation 11, which is shown here. So what I calculated was the capital N, which is the moles per gram. So I can put that number on the left side of the equation. So now is the tricky part, solving for this equation. And it helps if you can replace percent aluminum, which is a weird looking variable, with a normal looking variable like A. Then I'm going to multiply everything by 100. And that changes the left side to 4.224, and that eliminates the 100 in the denominator on the other side. And then I'm going to combine my A's so they look a little bit different, and then you can see I get 100 minus A on the right hand side. I'm going to distribute that times 0.015, and then I get my constants and variables, and I'm going to combine them, subtract 1.53 from both sides, and then combine my A's, and then solve for A, and I get 66.8%. So 66.8 is typed in, and I'm done. You will get different numbers. Do not use my numbers, but you can use the process. Hope that's helpful.